Okay, so in this video, we will consider additional examples of the determinant. So our first example, the determinant of the 2 by 2 matrix 1, 2, 6, 7. As always, when we have a 2 by 2 matrix, we know we can simply do AD minus BC. And so we'll have 1 times 7 minus 6 times 2, which gives us 7 minus 12, which gives us negative 5. And we're done. Just for the fun of it, let's see if we had used a row operation to get a zero entry. Suppose we take the matrix 1, 2, 6, 7, and what if we use now this 1 to kill the 6 below? So let's do row 2 minus 6 row 1. We know that this row operation will not change the determinant, so we'll have an equality. We can recopy row 1. Now 6 minus 6 is 0. 7 minus 6 times 2, 7 minus 12, negative 5. Now we have an upper triangular matrix, and so the determinant is quite simply the product of the diagonal entries. 1 times negative 5, which is just negative 5. Or if you think of it as AD minus BC, 1 times negative 5 minus 0 times 2, so it's just 1 times negative 5. What if we had used, instead of a row operation, a column operation? So let's start over with the original matrix, 1, 2, 6, 7. And now instead of killing the 6 with the 1, we'll kill the 2 with the 1, doing column 2 minus twice of column 1. This type of column operation also leaves the determinant unchanged. We can recopy the first column. 2 minus 2, 0. 7 minus 2 times 6, 7 minus 12, negative 5. And once again now, we have a 0 here. Now we have an upper triangular matrix. Everything above the main diagonal consists of zeros. And so we have the product of the diagonal entries, 1 times negative 5, which is negative 5. As before, or you can think of it in this way, AD minus BC, 1 times negative 5 minus 6 times 0, is just negative 5. This is just to show you an example of a row and a column operation, but every time that you have a 2 by 2 matrix, you can just directly use AD minus BC for its determinant. And that's it for a 2 by 2 matrix. Let's consider now a more interesting example with a 3 by 3 matrix. So we'll ask to find the following determinant of the matrix for negative 1, 6, negative 3, 1, 2, 2, 5, and 7. So first we'll find this determinant in a rather naive way. We'll go directly to the cofactor expansion. Now we know we can use cofactor expansion along any row or column of our choice. Let's use cofactor expansion along the first row. So this will be A11 times its corresponding cofactor, C11 plus A12 times its corresponding cofactor, C12 plus A13 times its corresponding cofactor, C13. Well, we know what the A's are. This is 4 times C11 minus C12 plus 6 times C13. Let us find the cofactors. So 4. Now 1 plus 1 is 2, which is even, so there is no negative sign, times the determinant of the matrix obtained from the original one after we delete row 1, column 1. If you delete row 1 and column 1, you have the matrix 1, 2, 5, 7. Minus 1, and now C1, 2. Well, 1 plus 2 is 3. 3 is odd, and so there is here an additional negative 1, because negative 1 cubed, 1 plus 2 is 3, is negative 1, times the determinant of the original matrix after deleting the first row, but now column 2. And we have the matrix, in this case, negative 3, 2, 2, 7. Finally, plus 6 times C1, 3. 1 plus 3 is 4. Negative 1 to the 4 is 1, so there's no negative sign, times the determinant obtained from A after deleting row 1, and now column 3. And we have the matrix now negative 3, 1, 2, 5. Now we're good to go. We can use AD minus BC for the determinants of all of these three 2x2 matrices. So we have here 7 minus 10, negative 3. Minus minus is plus. Negative 21 minus 4, negative 25. Plus 6 times negative 15 minus 2 times 1 minus 2, negative 17. So what do we have? Well, negative 12, negative 25. 6 times 17, well, 6 times 10 is 60. 6 times 7 is 42, so that's 102. So what do we have? Negative 37, negative 102, which gives us negative 139. Okay, so we have the answer. The determinant of this matrix is negative 139, obtained directly by cofactor expansion. This is too much work though. We can do much better if we use row or column operations to introduce some zeros, and go, instead of finding 3 cofactors, only 1. This was just as a warm-up to show that really this is too much work. Let's get some zeros in here. So let me recopy the matrix. We want the determinant of the matrix 4, negative 1, 6, negative 3, 2, negative 3, 1, 2. Let me just rewrite it. And 2, 5, 7. Okay, now let's introduce some zeros. Well, we have 2 1s, so this shouldn't be too hard. We can either, if we wanted to, kill off this negative 1 and this 5. We could also use this 1 with column operations to kill off the negative 3 and the 2 here. Let's do this. Let's use column operations to kill off these 2 entries. So we will do column 1 plus 3 column 2, and column 3 minus 2 column 2. These 2 column operations will not change the determinant, so we will preserve the equality. We are not changing column 2, so we can recopy it. Column 1 plus 3 column 2, so 4 plus 3 times negative 1 is 4 minus 3, 1. Negative 3 plus 3 is 0. 2 plus 3 times 5, 15. 17. Now we do column 3 minus 2 column 2. 6 minus 2 times negative 1 is plus 2, 8. 2 minus 2 is 0. 7 minus 2 times 5 minus 10, negative 3. And now we can use cofactor expansion along row 2. We know this would give us a 2, 1, C2, 1, but that's just going to be 0, plus A2, 2 times C2, 2, plus A2, 3 times C2, 3. But again, this will be multiplied by 0, so all we have is A2, 2, C2, 2. So we go from using 2 very simple column operations, having to compute 3 cofactors, to a single one. Well, A22 is 1, so it's just, that's it. 2 plus 2 is 4, which is even. Negative 1 to the 4 is 1, there's no negative sign. So all we're left is the determinant of the matrix obtained from the original one after we delete row 2, column 2. So all we have is 1, 8, 17, negative 3. This is a simple 2 by 2 matrix, and so we can use AD minus BC. 1 times negative 3, negative 3, minus 8 times 17 equals negative 3, minus, well, 8 times 10 is 80, minus 8 times 7, 56. 80 plus 50 is 130, 3 plus 6 is 9, so that's negative 139, as we have previously obtained. But if you notice, we had fewer calculations. We performed our 2-column operations at a single 2 by 2 determinant, and we were done. So it's always better to introduce zeros in a row or in a column and then compute, using cofactor expansion, a single cofactor. Never be satisfied unless you have, and by that I mean never use cofactor expansion, unless you have constructed a row or a column where every entry is 0 except for possibly one entry. Let's now do it again using, instead of column operations to start, let's use row operations. The solution will be equally elegant. So we have 4, negative 1, 6, negative 3, 1, 2, 2, 5, 7. Let me use this negative 1 to kill the entries below. So we'll do row 2 plus row 1. And we'll do row 3 plus 5, row 1. Both row operations will not change the determinant, so this will preserve our equality. We can recopy row 1 as we are not changing it. So row 2 plus row 1, negative 3 plus 4, positive 1, 1 plus negative 1, 0, 2 plus 6, 8. Row 3 plus 5, row 1, 2 plus 5 times 4, 20, 22. 5 plus 5 times negative 1, 0. 6 plus 5 times 6, 7 plus 5 times 6, 7 plus 30, 37. And now we have in column 2 all zeros but one entry, and so we use cofactor expansion along column 2. Again, we don't need to compute cofactors C22 and C32, as they will be multiplied by 0. So all we're going to be left with is A1 to C22. C12, sorry. First row, second column. Well, A12 is negative 1. 1 plus 2 is 3. Negative 1 cubed is negative 1. Times the determinant obtained from A after we delete row 1, column 2. And so we have 1, 8, 22, 37. This is positive 1, so it goes away. Now we have a 2 by 2 matrix. We can use AD minus BC. 1 times 37, 37. Minus 8 times 22. Well, that's 37. Minus 8 times 20, 160. Plus 2, 176. 37 minus 176, negative 139, as before. And so both solutions are equally short and elegant. Either you use column operations to get a row of zeros except for one entry, and then have a single 2 by 2 determinant, or use row operations to have a column where all the entries are 0 but one entry, and then use cofactor expansion along this column. Either way, you get the right answer in the same amount of work. And both solutions are better than the original one with cofactor expansion directly without introducing zeros. This really is not the optimal solution. Those two are much better. Let's do one last example now with a 4x4 determinant. In the case of a 4x4, we will not use cofactor expansion directly because if you think of it, this is a horrible idea. You will have 4 cofactors and they will each be determinant of a 3x3 matrix. And then you'll have to find all of those 4 determinants. So in a sense, if you find the determinant of a 4x4 matrix using only cofactor expansion, you'll have to do this amount of work 4 times. That is way too much work. So we'll jump directly to introducing zeros with the help of row and or column operations. So here's the matrix. 1, negative 2, 3, 1, 5, negative 9, 6, 3, negative 1, 1, negative 6, negative 2, 2, 8, 6, 1. And we want the determinant of this 4x4 matrix. Okay, well, there's a lot of ways to attack this problem. As always, we want to introduce in a row or a column all zeros except for possibly one entry. If you look here, we can use this 3 to kill the 6's. So we'll do row 2 minus 2 row 1, row 3 plus 2 row 1, and row 4 minus 2 row 1. All of these 3 row operations do not change the determinant, and so we preserve the equality. We can recopy the first row as we're not changing it. Let's apply the row operation. 5 minus 2, 3. Negative 9, positive 4, negative 5. 6 minus 6, 0. 3 minus 2, 1. Second row operation now plus 2. Negative 1 plus 2, 1. 1 minus 4, negative 3. Negative 6 plus 6, 0. Negative 2 plus 2, 0. Third row operation, minus 2 row 1, so 2 minus 2, 0. 8 minus 2 times negative 2 is plus 2, 4, so it's 12. 6 minus 6, 0. 1 minus 2, negative 1. Now in column 3, we have all zeros except for one entry, and so we use cofactor expansion along column 3. Well, all we're going to have is a 1, 3 times C1, 3. As all the other 3 entries are 0, we don't need to find their corresponding cofactors because once multiplied by the entries in A, they'll be killed. So what do we get? A13 is 3. 1 plus 3 is 4. Negative 1 to the 4 is positive 1, so there's no negative, times the determinant obtained from A after deleting row 1 and column 3. So we have the matrix 3, negative 5, 1. 1, negative 3, 0. 0, 12, negative 1. And now we have the determinant of a 3x3 matrix. Once again, we're not happy with just 1, 0. We will introduce one additional 0. There's a lot of options here. We could kill this 3 by doing row 1 minus 3 row 2. We could kill this negative 1 by doing row 3 plus row 1. Let's do it this way. So let's do row 3 plus row 1. This again will not change the determinant. So we'll have 3 times the determinant. We can recopy the first 2 rows as we're not changing them. 0 plus 3, 3. 12 plus negative 5, 7. Negative 1 plus 1, 0. Now we can use cofactor expansion along column 3. So we have our previous 3, don't leave that one behind, times A1, 3, C1, 3. Let's see. So 3 times A1, 3, which is 1, is just 3. 1 plus 3 is 4. Negative 1 to the 4 is 1. So we're left with 3. C1, 3 is a determinant of the matrix after deleting row 1 and column 3. And so we have 1, negative 3, 3, 7. Now we have a single 2 by 2 determinant, so we use AD minus BC. So 3 times 1 times 7, 7, minus 3 times negative 3, negative 9. So all we have is 3 times 7 plus 9, which is 16, which gives us 48. And that's it. So the determinant of this 4 by 4 matrix is equal to 48. Now, let's do it again using a different idea. We've used this 3 here with row operations to kill the entries below. Let's now use this 1 and column operations to kill these entries. And hopefully we'll arrive at the same answer. So our matrix is 1, negative 2, 3, 1, 5, negative 9, 6, 3, negative 1, 1, negative 6, negative 2, 2, 8, 6, 1. Okay, so let's use column operations. We'll do column 2 plus 2 column 1. Column 3 minus 3 column 1. And column 4 minus column 1. All of these 3 column operations will not change the determinant, so we preserve the equality. Let's recopy column 1 as we're not changing it. Alright, so column 2 plus 2 column 1. Negative 2 plus 2, 0. Negative 9 plus 10, 1. 1 plus negative 2, negative 1. 8 plus 2 times 2, 4, positive 12. Column 3 minus 3 column 1, so 3 minus 3, 0. 6 minus 15, negative 9. Negative 6, negative 3 times negative 1 is plus 3, negative 3. 6 minus 3 times 2, 6, 0. Finally, column 4 minus column 1, so 1 minus 1, 0. 3 minus 5, negative 2. Negative 2, negative, negative 1, negative 1. 1 minus 2, negative 1. So now, every entry in row 1 is 0 except for the first entry, so we use cofactor expansion along row 1. So we'll have quite simply A11, C11. A11 is 1. 1 plus 1 is 2. Negative 1 squared is 1. So all we're left with is the determinant of the matrix obtained from A after we delete row 1, column 1. So we have 1, negative 9, negative 2, negative 1, negative 3, negative 1, 12, 0, negative 1. Well, we already have 1, 0, so here we have two options. We could simply do column 1 plus 12 column 3 and make this a 0. Or we could do row 1 minus 3 times row 2 to kill out this entry and make this a 0. Well, we've used column operations just to shake things up. Well, let's now use a row operation. Row 1 minus 3, row 2. Again, this will not change the determinant, so it will preserve the equality. We can recopy the bottom two rows. So 1 minus 3 times negative 1 is plus 3 is positive 4. Negative 9 plus 9 is 0. Negative 2, positive 3, positive 1. So we can use cofactor expansion now along column 2. All we're going to get is A22, C22. A22 is negative 3. 22 negative 1 to the 4 is positive 1, so there is no negative, times the determinant obtained from the original matrix after we delete row 2, column 2. And so we get for 1, 12, negative 1, a single 2 by 2 matrix, and so we find its determinant using, as always, AD minus BC. We'll get negative 4, negative 12 times 1, 12. Well, what we get is negative 3 times negative 16, which is, as before, 48. Voila. So just to show you two different ways of finding out this determinant, and there are several more with the negative 1 here, here, and here with these two 1s. Every time you have a 1, you can take advantage of it and use it to kill the entries in the same column or in the same row. The lesson here, the final lesson, is never ever find the determinant of a matrix that is larger than just 2 by 2 with cofactor expansion directly. Always use a combination of row or column operations to introduce zeros everywhere in a row or column of your choice except for one possible entry, and then and only then can you use cofactor expansion. This will always give you the most efficient way of finding the determinant.